Hello, in this video I will be presenting our research paper titled, PointSplit, Towards On-Device 3D Object Detection with Heterogeneous Low-Power Accelerators. As everybody would agree, on-device machine learning could enable real-time and private ML applications. This means that we could potentially run complex models on our mobile or edge devices without relying on cloud-based computing. On-device machine learning evolved with the development of mobile heterogeneous processors. For example, mobile GPU widened the range of possible tasks on edge devices. Recently, another powerful accelerator, mobile NPU, is available, and neural networks, which are known to be computation-heavy, could also be carried out on edge devices. With this trend, now it is becoming more important to search for the potential of its expanded scope. As an example, we can think of on-device 3D object detection from indoor scene. This could be widely used on various applications in the upcoming era of mixed reality. We assume that 2D and 3D data are used together so that fine-grained features from 2D image would improve 3D object detection accuracy. However, 3D object detection with 2D images brings heavy and heterogeneous workloads to the system. Therefore, we need to find good workload allocation taking into account the different features of heterogeneous processors. Before we dive into our main idea, we'd like to introduce our baseline. First, 3D object detector. Many 3D object detectors leverage PointNet++ as a feature extractor to encode 3D features from the input point cloud. Within PointNet++, the points are sampled and grouped based on their local information. I will call these two operations combined point manipulation. After point manipulation, a neural network called PointNet processes the grouped points. Throughout PointNet++, this alternation of point manipulation and PointNet repeats. As mentioned earlier, we utilized 2D information on top of 3D data to improve 3D detection accuracy. For this we employed one of popular fusion method, point painting. To explain it further, let's consider RGB image and point cloud as inputs. Initially, we conduct semantic segmentation on the RGB image to obtain the segmentation results. Then, we project these results onto 3D point cloud. This process generates a painted point cloud. Finally, this painted point cloud is fed into 3D object detector, which in our case is VoteNet. Point painting is shown to improve the detection accuracy, but more computation burden is added to the system. Now, with our baseline algorithms, let's think about job allocation to processors. To summarize, there are three different operations in our baselines: point painting, point manipulation, and PointNet. Regarding processors, we consider two processors, NPU and GPU. NPU can run NN inference very fast, but its capabilities are limited to NN operations. In contrast, NN inference is relatively slower on GPU, but it can run wide coverage of operations. Thus, it is natural to run point painting and PointNet on NPU and point manipulation on GPU. But is this simple workload allocation enough to fully exploit the processors? Now, let's consider the scenario where we run our baselines on the environment with both GPU and NPU. The first step involves point painting, and as described from the previous slide, NPU is a better option for executing it. While NPU executes point painting, the GPU remains idle. After point painting is completed, we move on to the execution of PointNet++. Initially, the point manipulation is executed, followed by the execution of PointNet. GPU executes point manipulation, and NPU executes PointNet. While one processor executes its own job, the other processor remains idle due to the dependence of the jobs. This repeats throughout PointNet++. But, as you can observe, there is long idle time in each processor. In this situation, we may ask, can we optimize the algorithm to better utilize the underlying system? Another challenge of our work lies in quantization. Quantization is one of the most widely used technique for lightning neural networks. To briefly explain 8-bit integer quantization, first, real values are clipped and each real value is assigned to the closest integer ranging from 0 to 255. This reduces memory consumption and improves inference speed with marginal accuracy drop. Also, it is a required step to make use of some ASIC, for example, Edge TPU. We tested TF-Lite default settings to quantize our model from 32-bit floating point to 8-bit integer. However, we experienced significant model performance drop when default quantization of TF-Lite is used. We deeply investigated this, and found out that we need to take special care of quantization granularity. Now, let me introduce our main idea, PointSplit. We observed low utilization of system under naive combination scenario. To solve this issue, the first main idea is proposed: system algorithm joint optimization. Biased farthest point sampling and parallelizable feature extractor are two main components of this optimization. To solve the long idle time issue in naive combination scenario, we tried to make GPU and NPU run in parallel. We sampled M points to generate a single point set as the first step of PointNet++, but how about sampling 2-point sets with half the number of points? Then, we can make GPU and NPU run in parallel. For example, while NPU is running PointNet for the first point set, GPU can run point manipulation on the second point set. Now, the overall runtime schedule could be modified as following. After point painting is completed, we sample 2-point sets with half the number of points from the painted point cloud. Then, as described in the previous slide, we can parallelize the jobs. This, however, uses the same sampling technique twice and 2 identical point sets are populated. This will degrade the detection accuracy. In addition, there is still idle time at early stage of the process. To explore another sampling technique, let's review farthest point sampling. This is base sampling technique used in PointNet++. Let's assume there is a point set and we want to sample 5 points. First, we randomly select the point from the point set. Next, the second point is selected as the farthest point from the first point. To sample the next point, the minimum distance from already sampled points is calculated per each point. The third point is selected as the point having the largest distance from the already sampled points. This is repeated. Finally, 5 points are sampled. Now I will introduce biased farthest point sampling. This technique samples points biased towards painted points. The intuition behind this is that we use the information from semantic segmentation not only for neural networks, but also for sampling such as foreground boundary. Assume there is a point set and some of them are painted. The first point is randomly selected as normal farthest point sampling. Then the distance from the first point is calculated, but different from farthest point sampling, we make the distance greater if the point is painted. The painted point is considered farther and more likely to be selected as the farthest point. This is repeated, and more painted points are sampled compared to when normal farthest point sampling is used. Let me show you the illustration of the effect of biased FPS. From the input painted point cloud, the result of normal FPS is shown on the left. And the result of biased FPS is shown on the right. You can easily find that more painted points are sampled as a result of biased FPS. Biased FPS helps to obtain 2 complementary point sets and achieve parallelizable feature extractor. Also, this gives augmentation effect during training process. And now, let me introduce our parallelizable feature extractor. Initially, half of the points, which we call SA normal, are sampled with normal farthest point sampling. This job is performed by GPU. Concurrently, NPU runs point painting and generates the painted point cloud. Each processor can carry out its respective operations of strength, in parallel with the other processor. After first jobs are completed, GPU uses biased FPS from painted point cloud to generate SA bias point set, and NPU executes PointNet on SA normal point set. This process is subsequently repeated. As you can see, this results in reduced idle time in each processor and higher utilization ratio. Now we move on to our second idea. I mentioned before that large quantization errors were observed when proper quantization granularity is not considered. To solve this, we propose role-based group-wise quantization. In TF-Lite, the default quantization granularity is layer-wise quantization. To explain it further, let's say there is a neural network with lots of layers, and we would like to quantize layer M. If the distribution of values are like this, the clipping range is determined based on the minimum and maximum values from the entire layer. We quantized the base model with this default settings, but we experienced significant drop in model performance. We lost MAP of around 27. To analyze the issue, we investigated the distribution of values by channels. We found that the distribution is quite different by channels. In this case, channels having narrower distribution are poorly expressed, because only few integers could be used to express these channels. As an alternative, we can think of channel-wise quantization. Under channel-wise quantization, the clipping range is determined separately based on min and max values from each channel. This could improve the detection accuracy, but large number of quantization parameters are required, because now we need to retain the quantization parameters per channel, which is several hundred times more than layer-wise quantization. Then, is there any room for optimization? To answer this, we observed the distribution of values by channels. Shown on the slide is the distribution of activations by channel in the last layer of proposal module. Clearly, there are 3 groups of channels, and the distribution is highly different by groups of channels. We found that different channel roles given in model construction are the main reason for this difference. As you can see from the table, each group of channels correspond to different role group in the model. This is another example from voting module. Here, the first group corresponds to point features, and the second group corresponds to voting center coordinates. Therefore, the quantization granularity should be based on this role group. We call this role-based group-wise quantization. Now I will introduce our implementation details. We used Sun RGBD as our primary dataset and Skynet v2 as secondary dataset. Sun RGBD consists of RGBD snapshot images. In contrast, each scene in Skynet is reconstructed from hundreds of RGBD images. This is why we use Sun RGBD as primary dataset, which is more suitable for our target scenario. Next, model implementation. We used DeepLab 3+ for point painting. Also, we re-implemented 3D object detectors in TensorFlow and achieved comparable accuracy. This conversion is to utilize 8-bit integer quantization and edge TPU compiling supported by TF-Lite. This is our hardware platform for evaluation. We used Jetson Nano for mobile GPU and integrated Coral Edge TPU into it, via PCI Express. Let me explain our experimental results on detection accuracy. On Sun RGBD, VoteNet shows MAP of 56.9, and point painting improves MAP by 3.3. Our PointSplit further improves MAP by 1.2. Biased FPS helps training more robust model with its augmentation effect. Next, we compare the detection accuracy of 8-bit integer quantized models. If proper granularity is not considered, the model performance significantly drops. But our role-based group-wise quantization well preserves accuracy in PointSplit. To confirm the generalizability of PointSplit, we tested PointSplit on other heavier 3D object detector baselines rather than VoteNet. More recent 3D object detectors show better detection accuracy with heavier modules. Group-free 3D uses transformer modules, and RepSurf uses better input representation. PointSplit shows consistently better detection accuracy when combined with group-free 3D or RepSurf. Next, we test the impact of quantization granularity. Layer-wise or naive group-wise quantization results in significant amount of quantization errors. Channel-wise quantization reduces quantization error, but requires a lot more quantization parameters. Role-based group-wise quantization shows tolerable quantization error, while keeping the number of quantization parameters small. Now we will explain experimental results on latency. To inference a single scene from Sun RGBD using both 2D and 3D input, on GPU, it takes longer than 8000 milliseconds. PointSplit decreases the latency to 750 milliseconds or 11.4 times faster, while preserving comparable detection accuracy. On Skynet as well, PointSplit reduces the latency from 27,000 milliseconds to 1,100 milliseconds, or 24.7 times faster, while still preserving comparable detection accuracy. To conclude, we envisioned that in the era of multi-type accelerators, heavy 3D object detection task is viable on device when heterogeneous accelerators are utilized synergistically. But naive combination fails to fully exploit the processors. We propose a new 3D object detection framework, PointSplit, that provides system algorithm joint optimization. We devised PointNet++ into parallelizable structure and new sampling technique called biased FPS is proposed. Also, role-based groupwise quantization is proposed. With these techniques, we achieved 11 to 25 times latency reduction, while preserving accuracy. One thing to note about our work is that inter-processor communication overhead could be large due to alternating use of accelerators. But we expect this overhead will decrease, thanks to the evolution of unified processors, where memory is shared across heterogeneous processors. We hope that our work could be the stepping stone for other follow-up researches. This is the end of the presentation. Thank you for listening.